We've now learned about both rotation matrices and displacement vectors. We've learned that we can make a complete rotation matrix all the way from the base frame to the end effector frame by multiplying together each of the individual rotation matrices from one frame to the frame next to it. But we also learned that we cannot do this with displacement vectors. So what if we want to know things like the position of our end effector in the base frame? How could we find D03? It turns out that we can do that by combining the rotation matrix and the displacement vector together in one big matrix called the Homogeneous Transformation Matrix. The Homogeneous Transformation Matrix is represented by the letter H, and it tells us both the rotation and the position of one frame, N, relative to another frame, M. We build a homogeneous transformation matrix by simply plugging in the rotation matrix and the displacement vector like this. Now, since the rotation matrix is a 3x3 matrix and the displacement vector is a 3x1 vector, that makes this matrix not square. Right now, it has 3 rows and 4 columns. This will prove to be a problem when we try to multiply the matrices together. So, to complete the homogeneous transformation matrix, we have to add a row on the bottom that consists of 3 zeros and a 1, like this. Let me show you an example using the manipulator that we have built on our board. For this kinematic diagram representing the manipulator that we have built on our board, we had found the rotation matrix R01 to be this. And we had also previously found the displacement vector D01 to be this. We can now put those things together to make the complete homogeneous transformation matrix from 0 to 1 like this. Similarly, we had found the rotation matrix from frame 1 to frame 2 to be this. And we had found the displacement vector from frame 1 to frame 2 to be this. We can now put those together into the complete homogeneous transformation matrix from frame 1 to frame 2 like this. So how does this help us? It turns out that we can string homogeneous transformation matrices together in the same way that we can string rotation matrices together. In other words, we could find H02 by multiplying together H01 times H12. Do you see why this is useful to us? Once we've found H02, we can break it apart into its rotation matrix parts and its displacement vector part. Now, R02 we could get just by multiplying the rotation matrices together. But there's no other way for us to get D02 other than to calculate this homogeneous transformation matrix and then pull out D02 from the place where it is in the matrix. This is how we can tell the location of our robot end effector for any combination of angles θ1 and θ2. Let's see how this works by going back to our Python code. Open up Python idle and then open up the code that we've been working with up until now. We have some code that calculates R01 and R12 and then calculates R02 by taking the dot product of those two. We also calculate D01 and D12. This time, we want to use these parts to make the homogeneous transformation matrices. Let's start by commenting out this line that we had from last time to print D12. Now, I would like to construct matrix H01 from the parts that we already have, the rotation matrix and the displacement vector. We can do that by using the numpy function concatenate. We'll do np.concatenate. Then we will put in parentheses the two matrices or matrix and vector that we want to concatenate or stick together. We'll do R01, comma, D01. Next, I have to tell Python what direction I want to stick these together. In other words, do I want to put R01 on the top and D01 on the bottom? Or do I want to put R01 on the left and D01 on the right? If I would put the number 0 here, that would make R01 be put on the top and D01 be put on the bottom. I actually want R01 on the left and D01 on the right, and I get that by putting a 1 here. Now, I'm actually not quite finished with H01 yet. So far, I've only stuck together R01 and D01. I still have to put that row on the bottom that goes 0, 0, 0, 1. So I'm going to use the concatenate function again. H01 is equal to np.concatenate, and then in parentheses the two things I want to stick together. H01, comma, and now I want to make a row vector that's going to go on the bottom. 0, comma, 0, comma, 0, comma, 1. And then ending square brackets and ending parentheses. And now I'm going to do comma, and this time I'll put 0 because I want to put the 0, 0, 0, 1 on the bottom rather than on the right. Now the last thing we want to do is print out H01 to make sure that everything looks correct. Let's do print np.matrix, so it will format the matrix correctly, H01. Now, let's go back up here and uncomment the thing that says print R02, except let's change it to be print R01. And let's also uncomment this line down here that says print D12, but let's change it to D01. This way, we'll be able to see if our H01 matrix formatted correctly. It should have R01 in the upper left and D01 in the upper right. Now, I made a mistake up here a couple lines ago. We actually need to have two sets of square brackets around this row. We need one set of square brackets to indicate that this 0, 0, 0, 1 is a row. And then we need a second set of square brackets to indicate that this is a complete matrix or a complete vector, just this one row. Secondly, let's go back up to this print, and instead of just printing R01, let's print np.matrix R01 so that it formats this thing nicely for us to see. Lastly, I don't want R01, D01, and H01 to be printed all one after the other. I'd like to have a little bit of space between them to help me see what's what. One way to print a blank line in Python is to print the /n in double quotes like this. Let's do that same thing after each of these print lines so that we have one blank line after R01 and one after D01. Then click on Run Module. Let's take a look at this output and see if it looks correct. The first thing that printed is the rotation matrix. This rotation matrix we should see in the upper left-hand corner of the homogeneous transformation matrix, and we do see it there. Also, this displacement vector here we should see in the upper right-hand corner. And there it is. Our last row should be 0, 0, 0, 1. It looks correct. Okay, let's go back to our code and let's see if we can find the position of the end effector, D02. I'm going to start by copying these two lines that we used to get the homogeneous transformation matrix H01. And then paste it here. This time I want to get H12. And we'll get that by doing R12 and D12 and then changing this H01 to H12. Okay, so now that I have H01 and H12, how do I get H02, the homogeneous transformation matrix, all the way from the base frame to the end effector frame? I can get that by taking the dot product, just like I did back here for rotation matrices. Let's do H02 is equal to NP dot dot H01 comma H12. Then let's do print NP dot matrix H02. Back here, I'm going to comment out my previous print commands. But I'll leave the blank lines to help keep things separate. Now run your code. Alright, so we get a matrix here that looks like it could possibly be right. The last row is 0, 0, 1, just like it's supposed to be. The 3 by 3 matrix above that looks like it could be a rotation matrix, and the thing in the top right looks like it could be a displacement vector. But how can we really check our H02 to see if it's correct? Well, these three numbers here in the upper right-hand corner represent D02, that is the position of the end effector in the base frame. What we're going to do now is put in some actual numbers for A1, A2, A3, and A4, and some angles T1, T2, and run this code. We'll look at the position output here, and then we're going to use our PSOC to set the angles of the actual servos in our robot manipulator. We'll compare the output telling us the position of the end effector to the actual position of the end effector, and we'll see if they agree with each other. let's look back at this manipulator that we have built. And let's add on to this some kind of end effector that will help us determine the XY position of the end effector of the manipulator. In your kit, find the angle bracket that looks like this. We are going to attach this angle bracket. We want to attach the angle bracket to the linear bracket like this. I'm using the M3 screws, and you can either use the short screws or the long screws. Hold a nut underneath while you use the screwdriver to tighten the screw just a little bit. Next, find the marker bracket that looks like this. We want to attach the marker bracket to the angle bracket like this. Use 2 of the long screws for this purpose. Now, take your dry erase marker and take off the cap. Clip the dry erase marker into the marker holder. When you look down from the top, the marker should pretty closely line up with the center. It'll be off just a little bit. And later on, we'll learn how to account for this tiny bit of offset. But for now, this is plenty close enough for us to test our work. Later on, we'll learn how to make this marker go up and down all on its own by using a prismatic joint. For now, we'll make the marker go up and down just by pressing it down with our fingers like this. Next, we're going to measure some link lengths. We'll look back at our kinematic diagram to see which link lengths are called what. We'll start with measuring link length A1. In your kit, find the paper ruler that's marked both in centimeters and in millimeters. You can fold over the end so that we get 0 right at the end of the ruler. Now, tip your manipulator up, and here we can see A1 really well. A1 goes all the way from the board, which is defined as Z0, up to the top of the first link. This is about 5 centimeters. So back in our code, in our Python code, we're going to make A1 be equal to 5. Next, let's do A2. To measure A2, you need to imagine the axes of revolution in your manipulator. The axis of revolution for the first servo is right here. It's represented by this screw that you use to attach the servo horn. The axis of revolution for the second servo is also that screw that you use to attach the servo horn. We want to measure the distance from that screw, that is the axis of revolution of the first servo, to that screw, the axis of revolution of the second servo, only in this direction. So we don't want to measure diagonally here. We want to measure straight across. And that's a little bit difficult to do, but see if you can do it. Line up 0 with that first screw, and we want to go all the way over to where the second screw is, I'm going to position my camera more straight down from the top. I think you can see it more easily that way. There we go. So this distance is about 6 centimeters, maybe 6.5. So back in the code, let's make A2 be 6 centimeters. Next, A3 is the vertical distance from the top of this link where we stopped with A1 up to the top of this next link. We'll try to measure that. So that distance is about 5.5 centimeters. Back in our code, we put in 5.5 for A3. And lastly, A4 is going to be all the way from the axis of revolution of this servo, this screw, over to the place where this marker is. Now this marker is tilted a tiny bit in mine. I'm going to try and measure to the place where the marker tip is. So in other words, from the screw, if I would bring this down right there, to the marker tip is about 5 centimeters. So let's make A4 be 5. All right, next I'd like to plug in the PSOC, but if we plug it in now, the last code we wrote is going to run. So let's go back to our PSOC code and update our PSOC code first. Start by opening up PSOC Creator. Go to File, Open, Project Workspace, and then find the PSOC Creator workspace that we've been working on in the previous videos and click Open. We have 3 projects in this workspace: our introduction project, the LCD example, and then servos. We want the servos project to be active. If your project servos is in bold, we're good to go. If it's not in bold, right click on it and then click on Set as Active Project. Now, let's go look at the C code that we wrote in this project. If we scroll down to the for loop, we have theta 1 going between 2 different angles, then theta 2 going between 2 different angles. I just want to have in here one set of code that sets both of the angles for theta 1 and theta 2 and then does nothing else. So let's take this line of code that sets the angle for theta 2, copy it, and then paste it right here. Now I still want this CY delay to give plenty of time for my 2 servos to get to the target position. But all the rest of these lines of code I don't want right now. So highlight all these lines. And then if you click right here, comment selection, it will put all those lines of code as comments. So when I run this code, those lines will not run. But I also don't have to delete them, so I can go back and get them later if I want. Now let's pick some set of angles to send theta 1 and theta 2 to. Let's try 45 45. Click on Build, Build Servos. Make sure that it ends saying Build Succeeded. Now the next thing I want to do is program the PSOC, but I can't program it until I plug it in. And as soon as I plug it in, it's going to start running the last code I wrote. Now I don't want the servos to just start moving when I plug in the PSOC. So I'm going to find the cord that I have connected to power. I used a red one. It connects VDD to the power rail, and I'm just going to unplug that one cord. Then I'll plug in the USB cable to the PSOC. That way my servos won't just start moving right away. Now I want to program the PSOC. Click on the program button and make sure that the program finishes, and then go back and plug in this one VDD line. The two servos should move to the angles that you programmed in here. We programmed in the angles 45, 45. So I see that this looks pretty good. This first link is lined up pretty well with the 45-degree line on my board. So that really is 45 degrees. And this one looks like it's pretty good, 45 degrees also. Now, take your marker and press it down till it touches the board so that you can see where the marker is touching the board. Each of these marks is 1 centimeter. And we've already drawn in our X0 axis here, which I wiped away a little bit, and the Y-axis here. So we want to find out the XY position where this marker is touching. The X position is 1, 2, 3, 4. And the Y position where the marker is touching is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's touching at 4 in X and 10 in Y. Now let's go back to our Python code. Theta 1 was 45 and theta 2 was also 45. We run the code. Now the way this is printed out, it's a little bit hard to see. I'm going to make this screen a little bit bigger. There we go. Now it's easier to see. Remember that our displacement vector telling us the position of the end effector is in the upper right-hand corner. It's telling us that the marker is at 4.2 in the X direction and 9.2 in the Y direction. We counted and found out that the end effector is actually at 410. So we're within a centimeter of being correct here. We can also tweak our numbers a little bit to get a little bit more accurate. Up here, when we did A1, 2, 3, and 4, we were kind of unsure whether A4 should be 5 or 5.5. Let's try increasing it to 5.5 and then run this again. This time it says we're at 4.2, 9.7. And that is pretty close to where we actually are. Let's try another set of angles. Back in the PSOC code, let's try an angle of 30 and 90. Click on Program. And check to make sure that your manipulator actually did go to about 30, which is this line here, and 90. Let's see what Python says about the location of the end effector. 30, 90, run. Let's take a look at where the end effector actually is here. The x position is around 2, and the y position is about 1, 2, 3, 4, 5, 6, 7, 8, about 8. Our Python code says that the x position is about 2.4 and the y position is about 7.7. So again, we're correct to within about a half a centimeter, and that's about as good as we're going to get for now. We are now at the point where we are able to tell the location of the robot end effector given the values of the joints. This whole problem is called forward kinematics, and we've now completed it. Next time, we're going to move on to a different problem called inverse kinematics. This is the problem where we get to specify where we want the end effector to be, and we'll calculate the angles needed to get us to that position.